So our next speaker is Gaurav Jain from Freescale. His talk is on Assertions, a smart path to low power verification of complex SoCs. Gaurav is staff engineer at Freescale Semiconductors in India. He has 9 years of experience and expertise in SoC and IP verification, low power verification, and pre-silicon validation domain, and has experience with multiple industry standard protocols. And we're going to hear from Gaurav for the next 25 minutes. So over to you, Gaurav. Thank you.
Okay. Hi, everybody. Thanks, Mike, for the introduction. Today, I will be presenting on the low power verification of complex power intent in the next generation automotive SoC, which is targeted towards body and gateway applications with very low power consumption. SoC devices today needs to be highly integrated, multi-purpose, high-performance devices, along with highly optimized power consumption in order to support maximum uptime, low cost of operation, as well as being green in nature. To achieve this, designers are using techniques like power shutoff, dynamic frequency and voltage scaling, well biasing, etc. to ensure that the device operates within the power budget limits of each mode. This has significantly increased the verification complexity with a new paradigm of low power operation added to the normal functional verification and the need to check the device behavior in each mode. In today's presentation, we'll discuss on why and how the system Verilog assertions enabled along with the low power CPF simulations can provide a smart path to reduce the cycle time and the debug effort and help in achieving the robust low power verification. So the agendas for today's presentation is we will be going through an introduction of a low power mixed signal automotive SoC design and the associated low power verification challenges. And we'll also discuss the generic design areas which can be targeted as sweet spots for the assertions deployment targeted towards low power intent, followed by user and automatic low power assertions. And we'll also discuss low power design issues which were not using the low power assertions and followed by the future scope and conclusion. So here is an example of a low power mixed signal SoC having 3 power domains. The PD2 is the high performance domain with multiple cores. PD2 is the high performance domain with multiple cores and on-chip flash. Then we have the PD1, which is the low power subsystem having a lightweight core as well as analog and digital peripherals. PD0 is the always-on domain having the complex power management control and monitoring units as well as primary clock sources such as oscillators, IRCs, etc. And there are multiple pads in the design which can be associated with the switchable power domains as well as the always-on domain in the design. Now, the design supports multiple low power modes wherein we have the full standby mode in which the high performance PD2 domain as well as the low power PD1 domain both can be switched off and only the PD0 domain is alive. Then we also can have a low power run mode in which only the high performance PD2 domain is switched off, whereas the low power PD1 domain and the PD0 domain is active. So thus there are multiple low power modes which are supported by the design and the associated mode transition. Coming to the low power verification challenges, low power SoCs have a complex power management control unit and the monitoring unit as well as the extensive power switch fabric logic which forms the heart of the low power intent in any SoC and thus needs to be thoroughly verified. There are multiple low power modes possible, and the device behavior needs to be thoroughly checked in each low power mode and across the mode transitions, as well as the power getting and the power of operation of each domain needs to be thoroughly checked. The low power automotive SoCs have a significant amount of analog content like the on-chip voltage regulators, power switches, like precision ADCs and DACs, etc., which significantly adds to the verification challenge to verify the digital analog interface as well as the low power operation of the analog hard macros. Also, the seamless operation of low power peripherals across the mode transitions as well as various memory retention modes further adds to the verification effort. The low power design for test and testability, reset controllers, logic-based controllers in each power domain further increases the scope and the debug challenges for functional verification at the RTL level. Also, performance verification needs to be performed to check, to measure the mode entry and exit times, as well as to verify the accelerated low power mode exit schemes which are present in the device. Again, the mode entry abort scenarios due to early wake-ups or due to various resets which are present in the design needs to be thoroughly checked for all low power windows which are possible. So, an idea about the total number of verification scenarios can be easily gauged by an illustration in this table, and the total number of combinations which are possible for verification. So as you can see, the number of power domains and the power modes coupled with the number of system clock sources like IRCs, oscillators, PLL, and valid clock ratios like the clock ratio between the core clock, platform clocks, bus clocks, as well as the flash clocks. Then we also have multiple number of reset domains and reset types in the design, multiple number of system wake-up sources like NMIs, GPIOs, interruption memories, as well as n number of analog IPs and peripherals which are present in the low power modes. The total number of verification scenarios is a multiple of all these parameters, and on top of that we also need to have the abort scenarios as well. As the number of design components increases, the number of verification scenarios increases exponentially. Okay, coming to the assertion-based low power verification flow. So here we are going to discuss the generic design areas, which are identified as sweet spots for the assertions deployment in any low power SoC design. With the increase in complexity of the digital design, the reset architecture has also become very complex. Multiple resets are needed in a SoC to reset the various subsystems. The reset domain crossing can lead to issues like metastability, glitches, or other functional failure of the system. In order to avoid these issues, designers have the option to either use reset or to match the reset to QR timings, which is a significant overhead. Moreover, in a low power design where clock getting schemes are expensive to save power, the clock may be disabled accompanied with the assertion of reset. Thus, in this case, only an asynchronous reset will work. Thus, in our SoC design, it was ensured that the system clocks were gated during the period. It is critical to check this design behavior across all the resets in the system, and we were able to successfully deploy the low power assertions, the reset domain crossing behavior, and resolve all the crossing issues which can be present. Another common area where we deployed assertions was the reset crossing check to ensure that a correct reset is mapped for each output as per their low power domain for correct power of behavior. For instance, consider a low power peripheral which is lying in the low power PD1 domain and its reset is incorrectly mapped to the always on domain. Now, upon the low power mode exit, since this low power peripheral is not be reset, the power up behavior for this peripheral is taken. Then we also have a low power mode entry and exit protocol. Macro model low power protocol assertions to verify the sequencing and protocol for low power control signals. In our SoC design, we have macro models like Flash, which have critical low power control signals mapped to the always on domain, such as the Flash low power enable signals as well as the acknowledgement signals. And it is vital that to ensure that these signals do not have an inverse at any point of operation in the design. As well as we need to ensure the sequencing of these protocol signals as they form an integral part of the overall protocol. Okay, so then the next area where we deployed the assertions was the split rail memory clock gating sequence checks. In a split rail memory, we have a periphery logic and an array, and there is a sleep signal which is used as an isolation between the periphery and the array logic. It is recommended that the sleep, during the assertion or deassertion of the sleep signal, the memory clock should be gated, as generally these signals have very huge timing knobs. So such kind of design behavior can be easily checked with our assertion for different types of memories and memory cuts across the design. Next item is the isolations and the clock gating checks. The isolations can be asserted or deasserted on any protocol clock like the IRC, which can be asynchronous to the system clocks. Thus, if the system clocks are not gated during the assertion or deassertion of the isolation, there can be a glitch at the output of the isolation signal. Okay, coming to the next slide, isolation and reset sequencing checks. It is required that the reset to the power gated domain is asserted only after the isolation is asserted, as the latched value of the signal should be the functional value and not the reset value of the port, and as that may affect the protocol. So again, we can deploy assertions to check this behavior. In our SoC design, there are certain low power peripherals such as SPI, FlexScan, etc., which were required to operate seamlessly across the low power mode transitions, and thus it is required that the resets to these peripherals is not asserted or deasserted during the mode transitions. Again, we successfully deployed the assertions to check the reset behavior for the low power peripheral seamless operation. We also have a fine-grained clock gating scheme assertions for the low power modes, wherein within the low power mode we have another level of granularity wherein we can control and configure and gate the low power peripheral clocks by configuring the clock configuration registers. Again, we deployed the low power assertions here to check the fine-grained clock gating scheme for all the low power peripherals in the design. The power on reset generally is not synchronized in design with the assumption that the primary clock source would be available only a few cycles after the POR is released. So if such is the case in any low power SoC design, it can be again easily checked through assertions. DVS enablement checks. It is extremely critical that the dynamic voltage scaling mode is not accidentally enabled due to an incorrect operation of any low power signal in the design. Thus, it is required to check that the DVS is enabled only when it is intended to do so. Here are some of the user assertions which were targeted for low power verification. So here we have a voltage regulator and a power management unit low power protocol checker. This property basically checks that once you are in standby mode and there is a system wake up event, then following that within 0 to n cycles, both the PD2 switch as well as the PD1 power switch should be closed, followed by isolation deassertion, and finally the current mode should be the run mode. Another flavor is we have the SRAM low power protocol for sleep. This property is basically checking that the SRAM sleep signal, which acts as an isolation between the periphery and the array, is asserted prior to the opening of the switch, and thus ensure that the array contents are not corrupted and the array is isolated prior to the removal of power from the memory. Then we have the assertions for isolation and reset sequencing checks, as well as the reset domain crossing assertions, which we just discussed. We also have assertions for reset mapping checks, wherein we check that the reset of each IP is mapped to the as per their low power domain to ensure the correct power up behavior. Then we also have the isolation clock gating checks, which ensures that the system clocks are gated during the isolation, assertion, and deassertion. We also have assertions to check that all the macro models low power control signals, which are mapped to always on domain, are never in an invalid or an unknown state at any point of operation in the design. Okay, coming to the automatic low power assertions from CPF. So these assertions are automatically generated from CPF and covers the shutoff, isolation, and the retention controls are not in an unknown state, as well as the power up and the power off sequence assertions. Next, we'll discuss upon the low power design issues which were caught using the low power assertions. So the major category of the low power design issues were the low power protocol issues, the power gating issues, memory retention issues, system bring up issues, and the macro model design and integration issues, which we are going to discuss in the subsequent slides. So here is an illustration of a low power mode entry protocol issue. The system is making a transition from the full standby mode to run mode, and the intended behavior of the device is that the power shutoff condition should be deasserted followed by isolation removal. However, the actual behavior of the device was that the isolation was removed, the shutoff was deasserted, and the isolation was removed, and again shutoff was asserted with no isolation. This is because of an unexpected toggle on the shutoff condition because of a bug in the power management unit, which resulted in the corruption of the always on domain. So here, by having a simple assertion that the isolations are always asserted whenever the shutoff condition is true, can easily catch this kind of issues by clearly highlighting the source of the issue. Low power mode exit protocol issue. So this is another illustration herein the power management unit requests the switch to be opened, both the PD2 as well as the PD1 switch, and it gets a grant or an acknowledgement from the PD2 switch, upon which it removes the isolations without waiting for the PD1 switch done to happen. This sequence can be easily caught again by using assertions. Here is an illustration of a macro model low power entry protocol issue, wherein the memory sleep signal was asserted after the opening of the switch, and thus resulting in the memory contents to be corrupted and the memory array was not retained. And The intended behavior of the device after power up was the code to boot from the system RAM, but the boot up failed due to SRAM contents getting corrupted because of the late assertion of the sleep signal. Another example is the flash power connectivity issue, wherein the flash macro model low power enable signal was driven from a switchable domain instead of an always on input, and this was resulting in the corruption of the always on domain. Future scope, we are working on the formal based design connectivity verification flow to be enhanced for reset mapping checks, as well as the IFB based verification of the low power control logic. Conclusion, the dynamic simulation driven approach proves to be cycle time and debug effort intensive when it comes to catching the low power integration and design issues. Assertions targeted towards the low power verification can help to provide a smart path in reducing the cycle time and to help catching the issues early in verification. Assertions also provide useful coverage information in addition to a top-level system coverage on key signals to measure the verification completeness. They can also be used across the projects by creating the template properties. Assertions along with coverage mapped to the vPlan helped us to find many critical system level corner case issues which could have been catastrophic in nature and thus helped us to ensure robust low power verification. Thanks. I'm open for any questions.
Thank you, Gaurav. Appreciate that.
Okay, yeah, thanks, Gaurav, and apologies for the interruption. We just lost the web access for a little while, which meant nobody could hear you. So we have one question online, Gaurav. It's a question is, if the assertions are generated from the CPF, then you potentially have a single point of failure, and that you're generating the checks from the actual source of the CPF. Did you face that problem?
So basically, so there are basically two ways to tackle that issue. Either we need to update the assertions to be disabled when the shutoff condition is applied or when a power domain is true, when a power domain is shut off, or we can use this the tool capability. There is a tool switch which can automatically shut off the assertions when the associated power domain is switched off. Is that the question?
I think the question is more from the fact that if you generate assertions from CPF, then how do you actually check that the CPF is correct in the first place?
In our case, actually, we are using both the user and automatic assertions because in our design we were not having isolations embedded in the CPF, but it was embedded in the RTL itself. So for CPF, we have the other low power static tools such as CLP, which can be used to measure the correctness of the CPF.
Any questions in Sophia? I think we'll have to switch. Any questions in Sophia? No?
No, we don't.
Okay, thank you.